Okay, so let's look at some questions from the Module 3, Lesson 12 and Lesson 13 problem sets in this video. Both of these lessons are a little bit on the basic side. They're checking to see if you remember sort of the basic workings of the greater than or less than sign and just able to sort of build inequalities and use the basic properties of inequalities, which is sort of summed up here in the lesson summary. It says, when both sides of an inequality are added or subtracted by a number, the inequality symbol stays the same and the inequality symbol is said to be preserved. So what that means is just like equations, you can add or subtract to both sides of them and you arrive at a new true inequality just like we used to arrive at new true equations. And then when both sides of an inequality are multiplied or divided by a positive number, the inequality symbol stays the same and the inequality symbol is still said to be preserved. It just means it doesn't change. And this is still just the exact same as the properties of equality we used for equations. But then this last part of the lesson summary is sort of like the one big thing that I was saying in class the other day, hopefully you remember it, that when both sides of an inequality are multiplied or divided by a negative number, the inequality symbol switches from less than to greater than or from greater than to less than, and the inequality is said to be reversed. That's the one thing that's different between what we call the properties of equality and the properties of inequalities, is that when you multiply or divide by a negative, you got to reverse that sign. Okay, so question 1 says, for each problem, use the properties of inequalities to write a true inequality statement. So the two integers are -2 and -5. So a true statement we could write about that is that -2 is greater than -5. And I know that looks weird because 2 feels smaller than 5, but just remember that to be greater than another number means that it is to the right of it on the number line. So you could always look at the number line, which one's to the right, which one's to the left. The one to the right is greater. It says subtract -2 from each side of the inequality. So I'm going to subtract -2, which I would normally just write as +2 because subtracting a negative is the same as adding a positive, but I'm going to do it the way the problem says to do it. I'll subtract -2. And so if I have -2 minus -2, well, anytime you take a number and subtract itself from it, you're going to get 0. And then that's greater than, well, -5. I'm going to think of this minus a -2 as +2. So that would get me to -3 on the number line. And that's still a true inequality statement. 0 is greater than -3. And then part C says to multiply each number by -3 and then write a true inequality statement. So I think you should see that when you multiply by -3, the number you get on this side is no longer going to be greater than the number you get on this side, and so you're going to need to reverse that sign like we were just talking about. So I'll let you take care of that. Number 2, on a recent vacation to the, do people say Caribbean or Caribbean? I'll say Caribbean. Kay and Tony wanted to explore the ocean elements. One day they went in a submarine 150 feet below sea level. The second day they went scuba diving 75 feet below sea level. So write an inequality comparing the submarine's elevation and the scuba diving elevation. Okay, so, well, it's 150 feet below sea level. So to me, that's negative. I would think of it as the submarine went -150 and the scuba divers only went -75. And I've got to put a greater than or less than sign in between them that makes it true. Well, this is further to the left on the number line. So that means that it is less than. B, if they were only able to go 1/5 of the capable elevations, write a new inequality to show the elevations they actually achieved. So I think you could sort of interpret this problem two different ways. Are they saying that what they went is 1/5 of what they could have gone? Or are they saying that what would have happened if they only went 1/5 as far? I think that's what they mean. I think they're saying, hypothetically, what if they had only gone 1/5 as far as they did? What would those numbers be? So there's two ways I could do this. I could multiply both sides of this inequality by 1/5, but that's the same as dividing by 5, and I prefer to do it that way. So I'm going to divide both sides of this inequality by 5. Negative 150 divided by 5 is negative 30. And over here, negative 75 divided by 5 is negative 15. And this is still to the left of this number. So I can still use the same less than sign that I had. And then question C, I'll let you answer. And so now for part 3, it says, if A is a negative integer, so all these A's that we see in all these questions here, we just have to imagine that it represents any integer, but it has to be negative, so that we just think about what that means. Then which of the number sentences below is true? If it's not true, give a reason. So let's think about 5 plus a negative number is less than 5. I would say that's true, right? If you're starting at 5 and then you add something that's negative, no matter what that negative number is, it's of course going to wind up being less than 5. So I'm going to write true next to this one. And I'm being thorough and actually writing the whole word true. If you just want to put a T next to it, that's fine. All right, so the next one says 5 plus A is greater than 5. But remember, A is a negative number. There's no way you could take 5, add a negative number, and then get greater than 5. So I'm going to say false. It says give a reason. I'm not even really sure. I mean, the reason, I guess, would be what I just said. You can't add a negative to a number and have the sum be greater. It's not really a good succinct way of saying what I'm trying to say there. You get the idea though. So I'll help you out with a couple more of these, but then I'll let you finish it. So I'll skip down. How about 5 times A? So I'm looking at number F here. 5 times A is greater than 5. Now remember that A has to be a negative number. And if I take 5 and I multiply it by a negative number, well, that's a positive times a negative. The answer's got to be negative. And any negative number is going to be less than this 5, not greater than. So I'm going to write false. And I think that the reasoning on this one's more simple. Positive times negative equals negative. All right, so hopefully you get the idea on these. I'm going to move on to some questions from problem set 13 now. So it says, for number 1, match each problem to the inequality that models it. One choice will be used twice. All right, so this is checking our ability to read some words and then relate that to these inequalities over here that are all super similar, right? They all have the exact same numbers, just we need to know the difference between a greater than or equal to sign in A, a less than sign in B, a greater than sign in C, and a less than or equal to sign in D. So hopefully that shouldn't be too hard. It says the sum of 3 times a number and negative 4. So that's what all of these say. The 3x plus negative 4, that covers this part. The sum of 3 times a number and negative 4 is greater than 17. So to me, that should be a greater than sign, not greater than or equal to. It's just, it simply is greater. That's C. So I'm going to write a C over here. And then I'll skip down. Maybe I'll do the first one and the last one for you. It says the sum of 3 times a number and negative 4 is at least 17. So that's worded a little bit differently. If to say that something has to be at least 17 means that it could be greater than 17, but also 17 is good enough. 17 is at least 17. So I would say that this one has to be the greater than or equal to sign, A. So that's really good that actually we did those two, because you can see the difference between one that required the greater than sign and one that required the greater than or equal to sign. All right, if x represents a positive integer, find the solutions to the following inequalities. Okay, so x is less than 7. Oh, I remember this problem now. So this one's a little annoying. You are supposed to actually list out all of the possible solutions to each one of these. So like if x is a positive integer, but it also has to be less than 7, then the only options it could really be is 1, 2, 3, 4, 5, or 6, right? It has to be an integer, so that's the whole numbers. It has to be positive, but it also has to be less than 7. So those are the only 6 options that could actually satisfy the statement in question A. All right, let's try G. So it says that the positive integer divided by 3 has to be less than 2. So let's think about what numbers that could be. Well, 1 divided by 3 is less than 2, right? Because it's 1/3. That's less than 2. 2 divided by 3 is less than 2 because that's 2/3. 3 divided by 3 is less than 2 because that's 1. 4 divided by 3 is still less than 2 because that's 1 1/3 or 4/3. And 5 is, let's see here, 5/3. That's still less than 2. That's 1 2/3. I can't write 6 though. So if I wrote 6, 6 divided by 3 is 2, and 2 is not less than 2. If it had the little equal bar there, then I could write 6. So on all these, this is what you have to do. You have to like figure out which positive integers could satisfy the statement and then actually list them out. I don't think any of them require too much. Like I think they're all, if I remember correctly from having done this in previous years, they're all like, there's less than like 10 or so solutions. You shouldn't be listing out like hundreds of numbers or something like that. If you are, I think that means you're doing something wrong. All right, number 3. Recall that the symbol equal sign with a slash through it means not equal to. If x represents a positive integer, state whether each of the following statements is always true, sometimes true, or false. So x is greater than 0. Well, if x is a positive integer, then yeah, whatever x is, it's always going to be greater than 0 by definition, what a positive integer is. So I will write, I'll be lazy, I'll write AT for always true. Okay, so let's skip down to maybe like F. X does not equal 0. I would say that's another one that's always true because 0 is not a positive integer. So there's no way that if x is supposed to be a positive integer, then x can't be 0. So I would write always true on that one as well. And then how about this one, D? X is greater than 1. I'm going to write sometimes true on that one. Because if I think about all the positive integers, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to infinity, those are all greater than 1. But there's one positive integer, the number 1, that is not greater than 1. It's equal to 1. And so there's that one case where this wouldn't be a true statement, and so that's why this would be a sometimes true statement. As long as there's even one time when it's not true, then it's got to either be sometimes true or false if it's never true. All right, I'll let you go ahead and finish it from there.